Hello and welcome back. I want to talk about least squares solutions to a linear system of equations. Okay, let A be just an n by n matrix. Okay, then it gives us a system of linear equations. A x equals b. And as I said in the last video, if m is greater than n, we say it's overdetermined. And in general, so in a generic case, it might have a solution, but generically, it does not have a solution. Okay. So by generically, I mean it might have a solution, but the points where it has the case where it has a solution are really isolated. Okay. They're isolated cases, but like if you take a random matrix, it doesn't have a solution. Okay. So the idea is to find the best solution. Okay. So let's introduce the concept of a residual vector. So for x star, any vector in Rn, we consider a x minus b, ax star minus b, which we call the residual vector. Okay. And now we call a solution x star the least squares solution if the residual vector is minimal. Okay. So what do we mean by minimal? By minimal we mean it has minimum length. So Euclidean length. Okay. So how do we formulate this? So we say x star in Rn is the least square solution of ax equals b, provided the residual vector is minimal in the following sense, namely the norm, so the length of ax star minus b is less or equal than ax minus b for any x in Rn. Okay? So it's a minimal. What does that mean geometrically? Let me draw a small picture. So assume this is a range of A. Okay. Assume we have the zero vector somewhere here. Okay. And let's also let's denote by y star ax star. Okay. Similarly, y for ax. So this will lie in the range, okay? There's a definition of the range. So now assume we have given a vector b. Okay. So b might not, if b lies in the range of a, then we have an exact solution, okay? But let's assume b does not lie in the range of a, so it lies outside. Now we're looking for an x star. So basically for y, we first look for y star, which has a minimum distance to this b, okay? So what does it mean? It has a minimum distance if the difference is orthogonal to the range, okay? So if you're looking for y star, such that y star minus b is orthogonal to the range. Okay, so let me write this down in formulas. So y star minus b is orthogonal to the range of A. Okay, so geometrically, if y star minus b is orthogonal to the range of A, means that y star minus b is minimal, okay? Because the minimal distance is achieved once it's orthogonal, right? If it's not orthogonal, you can easily see the distances further. It's just elementary geometry, but you can also prove this algebraically. Okay, using this intuition, we now know what to do, okay? We have to find first y star, such that y star minus b is orthogonal to the range, and then we can solve. Once we have y star, because y star is a star x, we can solve, okay? So let's write A as follows. So A is an m by n matrix, so we write A as A1, A2, A3, until AN. Whereby A here we mean the columns, okay? So AI is the i's column of A. Okay. So by definition, the range is spanned by the columns, right? So by definition, note that R of A equals the span of A1 to AN. Okay. So if we want that y star minus b is orthogonal to the range, so we need that it's orthogonal to any of these vectors here, okay? So we want the following. We want that AI is orthogonal to y star minus b for I, 1, 2, 3, 4 till n. Okay? So this, what does this mean? If you write this in formulas, this means nothing else than AI transpose multiplied by y star minus b is 0. It's equivalent, okay? Again, for all I from 1 to n, okay? This is equivalent to A transpose. Take the whole matrix A transpose and multiplies by y star minus b being equal to 0 vector. The 0 vector in Rm, okay? Let me write this AT. Okay, here 0 denotes the 0 vector in Rm, alright? And because AT is an n by m matrix. Sorry, it's a 0 vector in Rn. Let's be careful. Because AT is an n by m matrix. Okay? A was an m by n matrix, so the transpose is an n by m matrix. Okay? So, okay. So we achieved, we want this to be 0. This to be 0, we can rewrite this as the following. A transpose y star equals A transpose B. Okay? But note that A transpose y star is just A transpose A x star. Okay? So, and this is again equivalent, right? So we ended up with a formula A transpose A x star equals A transpose B. Okay? So if you solve this system, it's a new system of no with n equations and n variables. If we solve this system, then we get a least square solution for the original system, okay? So let's write this down as some facts. Actually, I have enough space here. So some facts. First one, this system is always consistent, okay? A transpose AX equals A transpose B is consistent, always, okay? The reason is the range of A transpose and A transpose A is the same. So the second one, the second fact is what we derived above. So the solution, the least square solution of AX equals B are exactly the solutions of A transpose AX equals A transpose B. The set of solutions of least square solution of the equation AX equals B is exactly the set of solutions of the system A transpose AX equals A transpose B. Okay, that's again a linear system of linear equations with coefficient matrix A, T, A, and right hand side coefficients A, T, B. Okay? And note that this system has a unique solution if and only if this matrix is, because it's an n by n matrix, if and only if this matrix is non-singular, right? So it means the rank is n, okay? I said if the rank of A transpose A is n, it turns out that this is the same than saying that the rank of A is n, okay? By similar reason for which one holds, okay? So the takeaway message here is, the way it's least squares, I was doing this wrong. To find the least squares solution of a linear system AX equals B, we only need to solve the system A transpose AX equals A transpose B. Okay? So in the next video, we're gonna do an example. Thank you.